Hello, and welcome to Differential Equations. This is Lecture 11, Constant Coefficient Linear Equations. Last time, we talked about how the general solution of an nth order linear ordinary differential equation is a linear combination of n linearly independent solutions, right? And then the Wronskian is a determinant that helps us check that solutions we found are indeed linearly independent. Okay, this time, we're going to apply this to a case where we can actually solve. We're going to be solving constant coefficient. Linear equations. Okay, so let's start with the simplest examples. Okay, so the simplest example would be a linear equation of order 1 with constant coefficients. So constant coefficients is just saying that this, which is generally some coefficient function, is a constant. And we're going to be working with homogeneous equations all of this lecture. Okay, so this first order equation, we already know how to solve very easily. This is a separable equation. You write it in its usual form by putting the term without the derivative on the right-hand side. And then this we recognize is just an exponential function. Okay, so let's look at second order, but let's keep it as simple as possible. So I won't put any first order derivative term. Let's just look at this linear constant coefficient equation. Okay, so here we have three possibilities depending on the sign of A. If A is negative, then the general solution is some constant times e to the square root of the absolute value of A times t plus b times the exponential of minus square root of the absolute value of A times t. If A is equal to 0, well, if A is equal to 0, this just says second derivative of function is 0. So we're just looking at a polynomial of degree at most 1. And then if A is positive, then the general solution here is A times cosine of the square root of A times t plus b times sine of the square root of A times t. Okay, but we can make this general solution look a lot like the general solution we had over here if we remember Euler's formula involving the exponential and complex numbers. That's going to let us write this as some other constant, let's call it c, times e to the I times the square root of A times t, plus some other constant d, e to the minus I, square root of A times t. Right? So in this last step, we're using Euler's formula right, that says that e to the I theta t, where theta and t are real numbers, say, is equal to cosine of theta t plus I times sine theta t, right? So when you have the exponential of a purely imaginary number, then the real part of that complex number is cosine of theta t, and the imaginary part is sine theta t. Right, more generally, right, if you take the exponential of an arbitrary real number, and let's say you write it as mu plus I theta, and let's go ahead and put a t, because for us, t will always show up when we're solving ordinary differential equations, then you can pull out the real parts, so e to the mu t, that's just a real exponential, and then what's left is a imaginary exponential, so you end up with cosine theta t, and then the imaginary part is similar, you have e to the mu t times sine of theta t. Okay, so let's make the following observation. So far, and granted these are very few examples, but so far, the solution is almost always a linear combination of exponentials, right? So if a is negative, you get a linear combination of exponentials. If a is positive, you get a linear combination of exponentials, right? And it's only this case that's a bit different because we ended up with a polynomial. Okay, but in most cases, we just ended up with a linear combination of exponential functions. This observation is very powerful. By reducing the search for solutions of the nth order constant coefficient homogeneous linear ordinary differential equation to the search for which exponential functions to use, we reduce solving the ODE to solving the polynomial equation. Right? So how does that work? Well, the general equation we're considering is, right, so nth order linear constant coefficient. So that means we have the nth order derivative of y plus some coefficient times the n minus 1th derivative of y, right? And so on, some coefficient times the derivative of y, some coefficient times y, and we're looking at the homogeneous case, I'm going to put 0, right? And here, constant coefficient, so these Pn minus 1 up to P0, these are constants. Right, so this is the general equation we're considering. If we were to plug in y equal to e to the RT as our educated guess as to what a solution should be, you plug this into the left-hand side, we get, well, every time you take a derivative, you just bring down an r. So we're going to have a common factor of e to the RT. And then when we took n derivatives, we have r to the n. Then we have this coefficient, Pn minus 1. Then when we took n minus 1 derivatives, we have r to the n minus 1. Right? And so on. When we take one derivative, we have just r. And then when we took no derivatives, oh, sorry, I left out P1, P1 times r. When we took no derivatives, we end up with P0. Right? So if you plug in e to the RT as a possible solution to this left-hand side, here's what you get, right? So when is this going to be a solution? It's going to be a solution when this vanishes, since the exponential number vanishes. That's when this polynomial vanishes, right? So this polynomial is going to be key. We give it a name. We call this polynomial, or let's be explicit, we call the polynomial, right? So I'm leaving out the exponential factor. This is called the characteristic polynomial. Also called the characteristic equation of the ordinary differential equation, right? So as we just noticed, if R is a root of the characteristic polynomial, meaning you plug it in, you get 0, then e to the RT is a solution of the ODE. Okay, so let's do an example of how the characteristic polynomial solves, how finding the roots of the characteristic polynomial can solve the ordinary differential equation. Suppose we wanted to solve the following problem, where you have two derivatives of y minus 2 times one derivative minus 3 times the function itself is equal to 0. And so this is second order equation. So if we want initial conditions, we need 2. So let's say we have y of 0 is equal to 1 and y prime of 0 is equal to 4. Right? We want to solve this problem. Then, okay, what we just saw is that we should look for the characteristic polynomial and then try to solve it. So the characteristic polynomial here is r squared minus 2r minus 3, right? Which factors easily into r plus 1 times r minus 3, right? So its roots are r equal to 1 and r equal to 3, right? So because those are roots of the characteristic polynomial, we know that e to the minus t and e to the 3t are solutions. Let's say solve the equation. Since those solve the equation, so does, by the superposition principle, y equal to a times e to the minus t plus b times e to the 3t, right? For any constants a and b. Okay, so we just need to satisfy the initial condition. So plugging in the initial condition, we would have y of 0, right? Well, y of 0 would be just a plus b, and we need that to be equal to 1. Then y prime of 0. Okay, well, if I take the derivative, here I would get minus a e to the minus t plus 3 times b e to the 3t. And then we need to plug in t equal to 0, right? And I need that to equal to 4, right? So, well, actually, let's go ahead and say when you plug in t equal to 0, you get minus a plus 3b, and we need that to be equal to 4. Okay, so this is satisfied if, okay, what you could do, so we just need to solve this equation and this equation. So notice that if I were to add them together, the a's would cancel, and I would get 4b equals 5. And then I can solve for a from the first equation and get minus 1/4. Right, so if a is minus 1/4 and b is 5/4, this is satisfied. So the solution, I know it's the only one by the existence of uniqueness theorem, the solution is y of t equals minus 1/4 e to the minus t plus 5/4 e to the 3t. Okay, so you see that we wanted to solve this ordinary differential equation, or initial value problem in this case, and it came down to a polynomial equation because we have linear constant coefficient. Okay, now in this case, we know we have found the unique solution because on the one hand, this satisfies the equation, and we were able to satisfy the initial values. And we know from the existence of uniqueness that there's only one possible solution that does that. In fact, these two solutions we found are linearly independent. And so this linear combination is the general solution to this equation, right? As we recalled earlier, the Wronskian is a tool that lets us guarantee that. So let me write down what that looks like in this case. The two solutions that we found in this example, right, namely e to the minus t and e to the 3t, form a linearly independent set. So let's say they are linearly independent. This is an instance of the following fact of life. Suppose R1 to Rn are distinct complex numbers. Then the set of exponentials, so y1 of t equals e to the R1t up to yn of t equal to e to the Rn times t. This is linearly independent. Right? Of course, you could check that in many ways, but in fact, their Wronskian has a simple formula. Well, the formula itself is simple. Proving that this formula is true might not be as simple. We're not going to do it, but I'll just tell you what the formula is. The Wronskian is given by the exponential of the sum times the product I goes from 1 to n minus 1 of the product. J goes from I plus 1 to n of the difference Rj minus Ri. Right? So you have this exponential factor, which is never equal to 0. And then you have this product of differences of the numbers. And because the numbers are all distinct, these differences never vanish. Right? And so is never equal to 0. Right? We saw last time that if you plug in linearly dependent set of functions to the Wronskian, you get 0. So since we didn't get 0, they must not be linearly dependent. Okay, so what's the upshot? If we are given an nth order linear homogeneous ODE with constant coefficients, right? So let's write down the general case again. And its characteristic polynomial right? R to the n plus p n minus 1, r to the n minus 1 plus p1 r plus p naught has n distinct roots then the general solution of the ordinary differential equation is y of t equals some constant times e to the r1t plus so on, some constant times e to the r n times t. Okay, so in the case where you have n distinct roots, then you're all set. You found, once you found those roots, you have found the general solution, right? Because the Wronskian guarantees that these n functions are linearly independent. Okay, well, what if the polynomial does not have n distinct roots? Okay, well, let me remind you of the multiplicity of a root, right? So the number R naught is a root of the polynomial p of r of multiplicity k if r minus r naught to the k divides p of r, but r minus r naught to the k plus 1 does not divide p of r. Right? The fundamental theorem of algebra says that an nth order polynomial has n roots, counted with multiplicity. Well, here, let me be more explicit. It has n complex roots, counted with multiplicity. Right? So if you write down a polynomial with complex coefficients, then if it's nth order, it has n roots in the complex numbers, right? They might not be distinct. You might not have n distinct numbers to solve it, but if you count them with multiplicity, then there are exactly n. Right, so for example, we look at the polynomial r to the 6 minus 3r to the 5 plus 4r cubed. Right? This factors as r minus 2 squared times r cubed times r plus 1. Right? And so it's a sixth order polynomial, and it has 6 roots. If we count with multiplicity, right? 2 is a root. Of multiplicity 2, right? Because r minus 2 divides the polynomial twice, but no more. 0 is the root of multiplicity 3, and minus 1 is the root of multiplicity 1. Right, so altogether, when we count them with multiplicity, it adds up to 6. Okay, so if we don't have n distinct roots, then that means we have repeated roots. How do we find solutions when we have repeated roots? Okay, so let's take an example. Suppose, let's just go ahead and start with the polynomial, right? R minus 3 squared, right? That's r squared minus 6r plus 9. So this is the characteristic polynomial. Of second derivative of y minus 6 times the first derivative of y plus 9 times y equals 0. Okay, now since r naught equal to 3 is a root of the polynomial, we know that e to the 3t is a solution of the ODE. Okay, but it's a second order ordinary differential equation. We know we need 2 linearly independent solutions to solve it, to find the general solution. So how can we find another? Okay, well, we know that e to the 3t solves, so let's consider the function z of t is e to the minus 3t times y of t. Right? So, if y of t were e to the 3t, then I'm dividing by e to the 3t, so I would just get 1. Right? So this should really simplify it. let's see what happens for z, right? What equation does z satisfy? So the first derivative of z with respect to t by the Leibniz rule would be minus 3e to the minus 3t times y plus e to the minus 3t times the derivative of y with respect to t. Okay, now I don't really know much about the derivative of y with respect to t. What I know about is the second derivative. So let's go ahead and compute the second derivative of c. So from here, we would end up with 9e to the minus 3t y minus 6e to the minus 3t dy dt plus e to the minus 3t second derivative of y with respect to t. And if I factor out an e to the minus 3t, I get second derivative of y with respect to t minus 6 times the first derivative plus 9 times y, right? Which is exactly the differential equation we started with. So if y solves the ODE we started with, then z solves this much simpler equation, second derivative of z with respect to t is equal to 0, right? Because if y satisfies this and you plug it into here, then this is all 0, and so that's the second derivative of z equals 0. But if the second derivative of z is equal to 0, then we know exactly what z is. Z is the polynomial of degree at most 1. Right? But as soon as you know z, then you know y, right? Because you just multiply both sides of this equation by e to the 3t. So then y is e to the 3t times a plus bt, right? And so we could write this as a times e to the 3t plus b times t e to the 3t. Thus, one choice for the other solution we were missing is t e to the 3t, right? You have that solution, you have this solution. And we know this is the general solution because this is the general solution to this. And here we saw that those equations were equivalent. Right? So wonderful. If we have repeated solutions, at least here where it was just a one solution repeated twice, we've found what you do. You just multiply by t. This trick always works. Like what trick? Well, the trick was this one. Consider dividing by the exponential solution you have when you have a repeated root. Right? Here's the conclusion from this trick. If R0 is a root of the characteristic polynomial, of a linear homogeneous ordinary differential equation with constant coefficients, so it's a root of multiplicity k, then here, so it's a root of multiplicity k, so I should find k solutions of the differential equation corresponding to it. So here they are. take e to the r naught times t, then take t times e to the r naught times t, and so on until the kth solution would be t raised to the k minus 1 times e to the r naught times t. These are linearly independent solutions. Okay, now since the roots of the characteristic polynomial add up to the degree of the polynomial, as long as we count with multiplicity, we now have a recipe for finding n solutions of an nth order linear ordinary differential equation, and these solutions will be linearly independent. So once we found them, we have found the general solution of the ordinary differential equation. Okay. Now finally, I want to come back to Euler's formula. So notice that if R, say, is given by mu plus I sigma, and its complex conjugate R bar, mu minus I sigma, notice if these are both solutions of the characteristic polynomial, and they're not equal to each other, so the imaginary part sigma is not equal to 0, then we know that both e to the RT and e to the R bar times t are solutions of the ordinary differential equation. An equivalent pair of solutions are e to the mu t times cosine sigma t and e to the mu t times sine sigma t, right? Which have the advantage, I'll put the advantage in quotes, of not using complex numbers. But that is a real advantage because sometimes you're working in a situation where you want real solutions. And so even though you can find some complex valued solutions, it's still useful for you to be able to write down just real valued solutions. So why are these equivalent? Well, using Euler's formula, if you start with a e to the RT plus b e to the R bar times t, well, Euler's formula tells us that e to the RT is e to the mu t times cosine sigma t plus I times e to the mu t sine sigma t, while e to the R bar t is e to the mu t cosine sigma t minus I times e to the mu t sine sigma t, right? And so we can write this as some constant C1 e to the mu t times cosine sigma t plus some constant C2 e to the mu t sine of sigma t by just taking C1 to be a plus b over 2 and sorry, C1 should just be a plus b, and C2 should be I times a minus b, right? So writing an arbitrary linear combination of e to the RT and e to the R bar t is the same as writing an arbitrary linear combination of e to the mu t cosine sigma t and e to the mu t sine sigma t. So you may prefer, when you have complex conjugate roots of your polynomial, to use these real solutions as opposed to using these complex solutions. Okay. So we'll stop there for now, but let me mention that we will go over a few more examples of solving constant coefficient linear ordinary differential equations next lecture. All right, see you next time.